Last video we stopped at finding the cracking moment, where we found the last video we stopped at this mid-span moment and right hand support moments. Now we need to find the cracking moments. Now to find the cracking moment, we have these equations given here in the standards on page number 129, where we have these cracking moments given here. Please note, this is the force intended P equal to 0, because we don't have spray stress. Our equation become this Z bracket FCT dot F star prime take away sigma CS. So in that one we have to work out three parameters. Let's work out those three parameters one by one. Section modulus Z, that is B has square over 6. It's basically your gross moment of inertia over YT. So if you know your gross moment of inertia, we already calculated, and YT is the distance, let's say 190 divided by 2. If you work it out this way, it's also able to find it. Okay, otherwise it is BD square over 6. It is basically the same thing. If I have BD cubed over 12 for I, and this is D by 2, and if you D by 2, if you just work it out, this solution, which is the BD cubed over 12 times by 2 over D, so that will give you 6, and that will give you square, so that will give you BD square over 6. So I think that's BD square over 6. So we are using 1 meter strip, 1000 millimeters times 190 square. Depth of the slab is 190 square over 6, so that gives me this section modulus, millimeter to the power cube. Now characteristics of the concrete strength, tensile strength, we already calculated 0.6 times FCD, so it's 0.6 times square root 25 is 3. Sigma CS, I think they have an equation for sigma CS, that is called shrinkage tensile stress. Sigma CS, it has this equation 2.3 PW, that is copied here. Now in that one we need to look for a couple of parameters. PW is given here, which is the web reinforcement, tensile reinforcement is ACT over BD. Now this has no pre-stress, so we are taking APT equal to 0, cross section area of tendon. So please check my beam deflection videos, where we discuss the detail about this APT. So we take this APT 0, so AST over BD. Now tensile reinforcement, I think in the previous video I can show it to you, that in the previous video we got the area of tensile reinforcement 500 millimeter square, so that is 500 thousands, that's the width of the beam, and this is effective depth from the tensile reinforcement. In the previous video we calculated 159, it gives me 0.0031. PCW, that is defined here, which is the compression reinforcement in your web. We don't have any compression reinforcement, so we substitute that PCW equal to 0. So 2.5 times this PW, tensile reinforcement ratio, take away 0.8 times 0 over 1 plus 50 times this PW 0.031. Young modulus of the reinforcement 200 thousands, and the shrinkage strength is given in the example. Please check the first video of this series, where you will find this shrinkage strength, say 100 times 10 to the power minus 6. So you get 0.6 megapascals. Now we can use these cracking moment equations, that is given here, Z bracket FCT dot F prime minus sigma ES. Now FCT dot AF is this we just calculated, the section modulus we just calculated, tensile strength 3 megapascals minus this called, I think, maximum tensile stress, maximum shrinkage tensile stress. So that maximum shrinkage tensile stress is 0.9. So if you use your calculators, you will get this 12,63500 Newton millimeters. We need in a kilonewton, so divide by 1000, that will give me 12.6 kilonewton meters. Now once you calculate the cracking moments, I think we have all the required details to calculate the effective moment of inertia. Now effective moment of inertia at a mid-spans, I copied this equation here. 71 times 10 to the power 6 I crack. I think I can show it to you, where we calculate the I crack. 71 times 10 to the power 6, that I substitute 1 minus I crack. I gross, I think we calculate I gross, which is the I value, 571 times 10 to the power 6. In the previous video we calculate this I gross times by the cracking moment. In these videos we calculate this cracking moment 12.6 kilonewton meter over 12.9. I think we are working at the mid span, so at the mid spans we just calculate in the last video 12.9 kilonewton meters. So I substitute that value, you get 431 times 10 raised to power 6 millimeter power 4, but not greater than these values. I think there is a check here that we need to make it here. If your AST is less than 0.005, because we found that ratio was 0.0031, which is less than 0.05, so you should have this IE maximum. So that is basically your IE maximum 0.6 Ig. So if you substitute this Ig, which is the gross moment of inertia, 571 times 10 to the power 6 multiplied by 0.6, you get 342. So this value 431 is less than 342. That's this checks. I effective is less than I effective max. And please note, this value is I effective max, 0.6 I is given here. So it's okay here because 431 I effective is less than 342. So that is okay. I encourage students to go through this by themselves. They can calculate, exactly follow the same procedures, but here you have these moments here 19.5 at the supports, and probably you need to calculate those DN and all these procedures which I showed to you here, but that is at the supports. Please check my video for the deflections where we also calculate the I effective at the support. So if you follow the same procedures given here, you will get the I effective at the supports, which is 112 times 10 to the power 6. Now if you have two I effective, one for the mid span and another one for the supports, I think we need to take the average for continuous being. You need to take the half at mid span and half at continuous supports. So we take the half of the mid span, which is 342 times 10 to the power 6. So we take this half, 342 times 10 to the power 6, plus we take this I effective 112 times 10 to the power 6 over 2. It gives me 227 times 10 to the power 6. So that's I effective average. We're going to use it for the calculation of the deflection. So in the next videos we will calculate the short term deflection and long term deflection and delta total. Thank you.